So if you have attributes which characterize the problems in some sense, and the attributes are in this case C, C1, 2, and 3, and C1 prime and so on, and the demands are characterized by D1, D2, and so on. So if you assign the demands to the attributes where each of the collection of attributes constitutes a component. So in this example we have two components. One component is defined by the attributes C1, 2, and 3, the other one by the attributes C1 prime and so on to 3 to C3 sub 3 prime. Then you can use the demands by the subset relation for ordering the attributes. Of course, processing a problem with attribute C3 in this case is more difficult than processing an attribute C2 with these demands, because this is a subset of that. And the easiest attribute in this case is C1. So you easily can use the assigned demands to give a difficulty, to create a difficulty order of the attributes. So going further and checking what are the attribute and what are the components. One example for one of the problem components in our case is the method of drawing. Method of drawing in this case is a component, and this component has three attributes. The three attributes are drawing one ball, drawing multiple balls with replacement, and the third attribute is drawing multiple balls without replacement. And you easily can imagine, if we assign to these attributes the demands, then probably the attribute number 3 is the most difficult one, and attribute number 1 is the easiest. So that means the subset relationship of the demands constitutes the difficulty structure for the attributes, which are a part of the components of the problem domain. And if we combine these structures, then we get in our simple case, we get the problems. In this case, 2 times 3, that means 6 problem types characterized by the attributes. And we also get very easily, by a simple rule, which is called the dominance rule, the structure of the problems, because this rule says one problem should be together with another problem as a pair in the prerequisite relation if it's easier on one component and not harder on any other component. That's the rule for ordering these problems according to the order, the difficulty structure for the attributes. And finally, for our 6 problems, we come up with this prerequisite relation. A is the most difficult problem, F is the most easiest problem, and for this prerequisite relation, there is, in terms of one-to-one correspondence, assigned this knowledge space. So that means we, by this method, creating the prerequisite relation, we also get the definition of the knowledge space. That means the possible characterization of the students. We did the same, and I do not go into details regarding the structure of the demands. I told you the demands have two functions. One is they are the basis for deriving the prerequisite relation. The other function is the demands 0 to 10 are the basis for the lessons, for explaining the students, for improving their knowledge. And they also can be structured. I'm not going in detail how to do this. There is publication on this. And if we combine the structure for the problems and the structure for the lessons, we get this diagram which explains the whole structure of problems and lessons. And the idea of the system is that the student gets access to other lessons only if he or she is able to solve one of the critical problems. And so, for instance, you easily can see the process starts with the lessons 0 to 4, and you can get access to lesson number 1 after you already visited the lessons 0, 2, 3, 4. Then you get access to this lesson. You are ready for this. After that, you are ready to solve this problem F, or should be ready. And in case you are able to do this, then you get access to these lessons, and so on. So this is a more traditional type of didactical structure, which is more oriented to the type where private teachers in former times tried to teach. And if we go one step further, we also can ask ourselves, and we take the knowledge structure, the knowledge space, and we can ask which lessons are necessary in order to transform a knowledge state into another one. For instance, in order to transform this state into that one, we have to present the lessons 5 and 6. If we want to go to this knowledge state, we have to present the lesson number 9. So you easily can imagine how this system works, and it has been realized in the so-called RATH, R-A-T-H system, and it's available on our homepage. For the master students, we will visit this next Tuesday. So let's come to the next approach, the competence performance approach. And let me say that the competence performance approach was started developing in the 90s of the last century, more or less independently by 3 persons or groups. One is a former doctoral student of mine, another one is a team called Dünsch and Gediger, 2 Germans. One of them is now working in Canada, and the third person who was involved in this is Doyon. And the idea, the general idea is that we want to model the knowledge through latent competencies in order to explain the observed performances. So we add competencies to the performances, to the problems. And we have to combine, in some sense, or to be more correct, to map one of these sets into another one. And the one of these functions is the interpretation function, which assign to each item that subset of competencies which is necessary to solve the item. And we, on the other side, have the representation function, which, if we have the competence states, the possible competence states, assigns to each of the competence state the subset of items which are solvable in this state. If you compare this approach with the demand approach, here we have a direct assignment of the competencies or demands to the problems. In the demand approach, we had an indirect assessment of the demands to the problems. So the competence performance approach has some nice consequences. The interpretation and representation function induce the competence structure and the performance structure. The performance structure is, in other words, what we called in the knowledge space approach the knowledge structure. However, here we have to differentiate the knowledge which is latent and the knowledge which is observable. So we used another term for knowledge structure. We are now using the term performance structure. So you have to take into mind that knowledge space T is included in this approach, and we add the competence structure and assign it or map it by the two functions. If we also structure the competence structure, we can increase the amount of structure of the performance structure. So an increasing amount of structure makes, for instance, that the assessment is more efficient. And as I told you already, Corossi introduced this and others introduced similar approaches. So the approach can be seen as an extension of the knowledge space theory, and in some sense, using the competencies, it explains the empirical observed solution behavior of a student. The performance refers to the empirically observable behavior, and the competence refers to the theoretically founded entities according to the observable behavior. So we have two sets and two structures. We have the set of elementary competencies and a structure on this, which is the competence structure. And again, we have the competence states. And we have a second structure. The set is the problem set. And we have a performance structure with the performance states, and it's equivalent to what we already know about the knowledge structure and the knowledge states. And the interpretation function assigns to each of the items the competencies which are necessary to solve the item, and the representation function assigns to each of the competence state those items which are solvable in this state. Giving an example from Corossi, from elementary geometry, this is a problem, for instance, given A equals 5 centimeters, C equals 8 centimeters. What's the area A of this triangle? And so here we have another problem. And so Corossi used several of these problems.